So this is it. Standard 19 is the last standard that we have to talk about in chemistry. Standard 19 is all about equilibrium, and equilibrium can kind of be compared to running up a down escalator. If you've ever run up a down escalator before, you know that in order to keep in place, to keep yourself from moving, you have to be moving forward. Otherwise, if you stop, the escalator is going to carry you back down. And equilibrium is kind of the same way, where you're constantly in motion, but you're not really getting anywhere. We'll see what I mean in a second. And we've already seen examples of equilibrium at work, and what we've seen is physical equilibrium. And if you think back to when we were talking about solutions, aqueous solutions, one of the things about aqueous solutions is that there's constantly this dynamic going on where some of that liquid is going to be vaporizing and some of it is going to be condensing. So some of those molecules are going to become a gas, and some of the gas molecules are going to come back down and become a liquid. This is why evaporation happens. When a glass of water evaporates, it's because the vapor pressure is greater than the atmospheric pressure, and so all of that liquid evaporates. But if you put it into a sealed container, you can stop water from evaporating. It'll vaporize a little bit if you suck out all of the air from that container, but eventually it'll reach a point where the vaporization rate, the rate at which the liquid molecules become a gas, equals the condensation rate, the rate at which the gas becomes the liquid. And so there's still molecules vaporizing and condensing, but they're doing it at exactly the same rate, which means there's no change in the water level. And reactions can work in exactly the same way. There are a lot of different reversible reactions out there, reactions that can go both backwards and forwards. For example, nitrogen and hydrogen can come together to synthesize ammonia. Okay? And this double arrow here indicates that this is a reversible reaction. And in a reversible reaction, you're pretty much always going to have some ammonia and some of your reactants, some of the reactants, some of the products. And which one you have more of depends on the conditions in which that lies. So, for example, the synthesis of ammonia going forward in this reaction towards the right is an exothermic process. It releases energy. And so the reverse is going to be endothermic, which means you have to absorb energy to break apart ammonia. So if you add a lot of heat to your sample, more heat means that it's going to favor the endothermic direction, that you're going to have more of your the left side of the reaction. And similarly, if you cool that sample off, you're going to find more of the right side. So where the equilibrium lies is, and the point of equilibrium is that when those things are in balance, when there's no longer a change in those relative levels happening. There's still reactions going forward and backward, but the rate at which those two things are happening is exactly the same. You can kind of think of it like a tank of water as well. So imagine there's a tank of water with a faucet and a faucet running into it, or maybe like a bathtub with a drain. If the faucet allowing water out is equal, the rate at which is flowing into the container, then you're not going to have any real change in the water level. If water is leaving just as quickly as it's entering, there's going to be no change. But we can shift where that water level lies by opening up one of the valves just a little bit more, and that'll cause a change in that water level. But eventually, it'll reach a point where it kind of balances out. Another example you can think of is two ants moving rocks between piles. So you have one ant carrying a rock forward and then another ant carrying rocks back to the other pile. And it doesn't really, the two piles aren't necessarily going to be the same size. The only thing that matters in equilibrium is that they're carrying them forward just as quickly as they're carrying them backward. And so mathematically, we can express this by using an equilibrium expression. We call that equilibrium expression K. Okay? Sometimes you'll see little subscripts down here like KEQ stands for equilibrium, or KW stands for water, and certain reactions have special K values. But for the most part, K in general is that equilibrium expression, which is just, you can think of it as the concentration of the products divided by the concentration of the reactants. So for example, if you had this kind of skeleton equation with A, B, C, and D all being elements or molecules, and then your coefficients being N, M, X, and Y, you would express your equilibrium expression as the concentration of C and D, okay, the right side, the product side of your equation, raised to the power of their coefficients. So C has coefficient X, molecule C has coefficient X, so you raise it to the X power. And you put that over the left side of the equation. with molecules A and B raised to the power of their coefficients. So let's say, for example, in this reaction, the pH reaction, there is a balance between, and one of the things we said is that water continually goes through this reaction where one hydrogen will leave a water molecule and form a molecule of hydronium and a molecule of hydroxide. And so we can express the equilibrium in this reversible reaction because it goes in both directions. The hydronium and hydroxide can make water again. We can express this as the concentration of the right side divided by the concentration of the left side. Okay? So the concentration of hydronium times the concentration of hydroxide, and since neither one of those has a coefficient in the balanced equation, we don't have any exponents there, divided by the concentration of the water squared, because that 2 is the coefficient for water, so we square that. So let's say, for example, if the pH of a solution equals 7, one of the things that we said is that the hydronium and the hydroxide will have exactly the same concentration. Okay, so 10 to the minus 7th would be the concentration of hydronium and hydroxide. And when it comes to the concentration of water, we can't really talk about the concentration of water because water is more or less a solvent. So since it's the solvent, we can't really talk about its concentration in that context. Okay, but what we can say is that when we multiply 10 to the minus 7 times 10 to the minus 7, we would get 10 to the minus 14th, which is that incredibly special value. Sometimes we call this Kw. Okay, and this is why the pH scale only goes up to 14, because in this equilibrium expression, as one of these values increases, the other will decrease proportionately, so that the equilibrium constant will always be the same for water, 10 to the minus 14th. Okay? We can also use these equilibrium expressions to determine whether we have more of the left side of the reaction or more of the right side. So let's go back to that example we were talking about where nitrogen and hydrogen can come together to make ammonia, or ammonia can decompose into nitrogen or hydrogen. To write an equilibrium expression for this reaction, we would take the concentration of the right side, the ammonia. Okay, so concentration of ammonia squared, because in the balanced equation the coefficient is 2. And we divide that by the concentration of nitrogen, and since it has no coefficient, there's no exponent there, times the concentration of hydrogen, which, since there's an exponent or a coefficient of 3 here, the exponent here would be 3. So plugging in some values to figure out what this K value actually means, let's say the nitrogen concentration is 0.2 molar and hydrogen concentration is 0.2 molar and ammonia concentration is 0.2 molar. Let's say the concentrations of all three things is exactly the same. What would that look like? Well, when we plug those values in, we take the concentration of ammonia, the concentration of nitrogen, and the concentration of hydrogen and plug those all into the equation, we wind up with a value of 25. Well, that value doesn't really have any units, but what it does tell us is that the equilibrium is going to lie to the right side of the equation. What that means is that we have a lot more ammonia than we do nitrogen and hydrogen in terms of the equilibrium. Okay? And anytime your K, your equilibrium value, is greater than 1, that equilibrium is going to, as we say, lie to the right. Okay, so ammonia, or the right side of the reaction. So what would it look like if the equilibrium lied to the left? Well, we can take a very similar equation, same equation, and we'll just change our values a little bit. Let's say the nitrogen concentration is 0.4 molar, the hydrogen is 1.2 molar, and the ammonia is still 0.2 molar. And so when we plug those into our equilibrium expression, okay, the 0.2 from ammonia comes down where the ammonia concentration goes, squared, divided by 0.4, which is the concentration of nitrogen, times 1.2 cubed, which is the concentration of hydrogen raised to the power of its coefficient. And when we do that, we get a value of 0.058. This value is less than 1, which tells us that the equilibrium is going to lie to the left side of this reaction, which means you have more of the nitrogen and hydrogen than you do of the ammonia. Okay? And so notice here it's the same reaction, it's just different conditions, different concentrations. Okay? And whether the equilibrium lies to the right or to the left doesn't necessarily depend on the equation itself, but more on the conditions in which that reaction is occurring. And so to create a generalization, when the equilibrium expression is greater than 1, we would say it lies to the right. If it's less than 1, we would say the equilibrium lies to the left, and if it equals 1, it means that both sides of the reaction are balanced. Now, it'll very rarely actually equal 1, but the point is that we can see this mathematically in that in order for this ratio to be greater than 1, whatever's on top has to be bigger than whatever's on bottom. Or vice versa, if we divide by a larger number than we have on top, we're going to wind up with a number that's less than 1. So your left side of the reaction would be greater than the right side of your reaction. Okay? Now, which way that equilibrium shifts is dictated by Le Chatelier's principle. Okay? Le Chatelier's principle states simply that equilibrium can be shifted by changing conditions like concentration, temperature, and pressure. And you notice a lot of these conditions are actually very similar to what we saw in rate of reaction. In general, things that speed up or slow down a reaction will also change an equilibrium expression. So going back once again to the nitrogen and hydrogen making ammonia example, not only can we change the temperature as we discussed earlier, but another thing that we can change is the pressure. Because if you look at the molecules in the beginning and in the end, we have 1 molecule of nitrogen and 3 molecules of hydrogen. That's 4 molecules. And according to ideal gas theory, those 4 molecules are going to want to take up a lot of space. Okay, they're going to exert a high pressure. They're going to want to take up a large volume. But in the right side of this reaction, we only have 2 molecules of ammonia, which means that they fight to take up far less space as long as they're a gas. So if we put this under very high pressure, these conditions, we pressurize it, it's going to favor more on the right side of the reaction where there's fewer molecules and those molecules are stuck together. Another example, again going back to the temperature example, there's a reaction reversible between nitrogen dioxide and dinitrogen tetroxide, okay, where 2 nitrogen dioxides will come together to form an N2O4 and vice versa. And depending on which way the reaction goes, part of it is dependent on the temperature of what's the conditions. So if you have very hot water, in general it will favor the 2 NO2s because as it is adding heat, the endothermic process becomes more favorable and the equilibrium would lie to the left. Okay, your K value would be less than 1. Okay. On the flip side, if your K value is greater than 1, like in the case of if you take the exact same sample and put it into ice, you're going to wind up with a lot more N2O4 because that's the exothermic reaction, and that ice will be sucking that energy away from the reaction.